Welcome to The Explainer. Today, we're jumping straight into a fascinating journey covering the absolute foundational components of modern electronic communication. If you've ever wondered how your devices seamlessly transmit and receive information through the airwaves, well, you're in the right place. We're going to unpack the brilliant engineering behind sinusoidal oscillators and the ongoing quest to create the perfect wave. Okay, let's dive right into this. We've got a roadmap today that breaks this complex electronics theory down into 5 logical steps. We'll start with the magic of oscillators, peek inside the tank circuit, explore the power of positive feedback, look at real-world LC and RC oscillators, and wrap up with a crystal oscillator revolution. Section 1. The magic of oscillators. Let's start by looking at the fascinating process of DC to AC conversion. To really understand why this matters, think about this for a second. How does a radio tune into just one specific frequency out of literally thousands? The answer lies in an oscillator's ability to convert direct current, or DC energy, into perfect, continuous alternating current sine waves. In the world of radio and television, we call these generated waves carrier waves. They're basically the invisible highways that carry audio and video data right to your devices. And the crazy thing? An electronic oscillator generates them continuously without any rotating mechanical parts whatsoever. It is completely silent and just incredibly efficient.
But generating these waves? Yeah, it comes with a major challenge. There are essentially 2 types of electrical oscillations we deal with: damped and undamped. Damped oscillations are kind of like plucking a guitar string, right? The amplitude just goes on decreasing with time because energy is lost to electrical resistance. The wave just naturally fades away. Undamped oscillations, on the other hand, maintain a constant amplitude over time. So our core problem in electronics is figuring out exactly how to keep that wave going constantly without letting it die out.
Section 2. Inside the tank circuit, the electrical pendulum. To actually generate a continuous wave, engineers use a simple oscillatory circuit, pretty widely known as a tank circuit. This consists of a capacitor and an inductor coil connected in parallel. You can think of it exactly like a mechanical pendulum. In a physical pendulum, energy swings continuously back and forth between potential and kinetic states. Well, in our tank circuit, the energy swings back and forth between the electrostatic field of the capacitor and the magnetic field of the inductor. It creates this beautiful continuous sequence. First, a fully charged capacitor completely discharges its electrons through the inductor. Second, this flow of current creates a maximum magnetic field right around the coil. Third, once that capacitor is empty, the magnetic field begins to collapse, and that produces a counter-electromotive force. This force actually pushes current in the exact same direction, charging the capacitor back up but with the opposite polarity. And finally, in step 4, the newly charged capacitor discharges again, but this time in the reverse direction. This constant, rhythmic swapping of electrostatic and magnetic energy is exactly what creates our alternating current. Section 3. The power of positive feedback. Overcoming energy loss. Now, here's the catch. Because the tank circuit is constantly losing a little bit of energy to resistive friction during every single cycle, that electrical pendulum we just talked about, it'll eventually swing to a stop. We need a way to give it a perfectly timed push. The solution is an amplifier utilizing positive feedback. To keep the wave undamped and continuous, we take the output of our oscillating circuit, amplify it, and feed a portion of it back into the input. But it absolutely must be positive feedback, meaning we're supplying energy of the correct polarity, completely in phase with the original signal, and at the precise time intervals needed to replace the exact amount of energy lost to resistance. And we aren't just guessing here. This is an exact science, governed by something called the Barkhausen criterion. This is the mathematical condition for continuous, undamped oscillations. Think of it as a super strict Goldilocks rule. If your feedback loop provides less energy than is lost, the wave dies out. If it provides more energy than is lost, the wave grows completely out of control and distorts. It has to be perfectly, exactly balanced.
So the crucial point here is this simple but massive equation: MV times AV equals exactly 1. AV is the voltage gain of the amplifier, and MV is the fraction of that voltage that gets fed back into the circuit. When the product of those 2 numbers equals precisely 1, boom! You've achieved the holy grail of perfectly sustained continuous oscillation.
Section 4. LC and RC oscillators. Looking at real-world circuits.
So how do engineers actually build these things in the real world? Let's quickly contrast the two main families. LC oscillators use inductors and capacitors, just like the tank circuit we discussed earlier. They are absolutely phenomenal for generating high-frequency radio waves. But if you try to use them for low audio frequencies, the inductors have to be massively bulky and expensive. That's exactly where RC phase shift oscillators come in. They swap out those heavy inductors for simple resistors and capacitors, which makes them perfect for low frequencies. Though their main drawback is that they generally have a smaller output, and getting the oscillations to actually start can be a bit tricky.
A brilliantly elegant real-world example of this concept is the Hartley oscillator. It uses a single capacitor connected in parallel with two inductors that are tapped right at their center. By tapping the inductors and tying that center point to ground, the circuit ingeniously creates the vital 180-degree phase shift required to feed the signal back into the transistor in perfect phase. It's just a remarkably clever piece of engineering.
Section 5. The crystal oscillator revolution. The ultimate stability.
Now, early engineers faced a really fatal flaw. As LC and RC circuits warmed up, their components physically changed, which caused their frequencies to drift. In radio broadcasting, where frequencies must remain pinpoint accurate so stations don't bleed into each other, this drift was just completely unacceptable. To solve this, engineers actually turned to nature, leveraging the incredible Q factor of crystals. The Q factor measures the quality of a resonant system, essentially how perfectly it rings like a bell without losing any energy. As this quote notes, a standard LC tank circuit might have a Q factor of about 100. A crystal? It can easily boast a Q factor of 10,000. That is a literally staggering leap in stability. The MVP here is the quartz crystal, which is inexpensive and naturally forms in these cool hexagonal shapes. Quartz exhibits something called the piezoelectric effect. If you apply an alternating mechanical strain to it, it actually produces an AC voltage. Conversely, and this is the most important part for us, if you apply an AC voltage across it, the rock itself vibrates mechanically. It essentially acts as a hyperstable microscopic pendulum. Now, what's really interesting here is the equivalent electrical circuit. When you place that vibrating piece of quartz between two metal plates, electrically, it completely stops acting like a rock and starts acting exactly like a highly precise LC series parallel circuit. The mass of the crystal acts like an inductor, its elasticity acts like a capacitor, and mechanical friction acts as a tiny resistor. Piezoelectric crystals totally revolutionized electronics by finally solving that quest for perfect stability. Let's summarize exactly why. They're cheap and incredibly abundant. They lock in frequency stability to changes of less than 0.1%. Because their frequency is dictated purely by the physical thickness of the crystal cut and not by those temperature-sensitive electrical coils we talked about, they are practically immune to normal heating. With Q factors reaching up to 26,000, they became the ultimate heartbeat of modern electronics. Which leads us with this final, kind of wild thought. Look around you right now. From the smartphone in your pocket, to the computer on your desk, to the Wi-Fi router sitting on your shelf, every single one of them relies on an oscillator to communicate. How many millions of these tiny, perfectly cut, vibrating quartz rocks are silently keeping time in the devices around you right this very second? It's a profound reminder that the most cutting-edge communication technology we rely on every single day is ultimately powered by the physical properties of the Earth itself. Thank you so much for joining me on this explainer, and keep exploring.